All right, let's see if this works. Maybe I'll zoom in a little more. But you're really gonna need it on full screen anyways. It's on a 4K screen, so it's huge for me. Um, right, so I figured I would um, try streaming a debugging session just to kind of give people a sense of what it's like to debug on Urbit and what are what's the normal workflow for that, the techniques for that, the general attitude around it. Which, if I had to summarize, it would be basically if you see a problem, dig into it and find the problem, um, which is often not what you want to do on like normal Earth software because the problem is likely to not be in your code. It's likely to be in some code beneath yours, in some library, or in some in your language runtime or any kind of thing. Um, and so on Urbit, you can't think that way, right? We pay quite a price for rebuilding everything, for reinventing everything. But if you're going to pay that price, you need to go ahead and take advantage of the benefits it does give you. Joe Duffy talks about this a lot in his blogging about Midori. Uh, that was a greenfield operating system project, and they were able to take a lot of advantage of that fact. Highly recommend that series of blog posts. They're just excellent. Um, this is really a trial run, not streaming, just recording to see if I like this way of doing things. See if I can still be productive. And the yeah, the case that I want to work on is the curious case of bar pack. So if I start up a ship, this is a localhost copy of wikdev wiswrite. You can look at its memory usage, and the issue. So what we're looking at here is, the main thing we're looking at. This is everything that's in Arvo. This is stuff that's not in Arvo, including for some reason 270 megs in cold jet state. I don't understand that, um, but appears to be there. The top line numbers are that we're using 942 megabytes of RAM, marked and sweeped. That's two different ways of counting it. They should come to the same thing. If they don't, that's a problem. Um, and then we have 500, about 600 megabytes in free lists, which means that it's within, like it's kind of mixed in with the memory that we're actually using. Like as in the memory we're actually using is fragmented, right? There are sections that we're using, not using, alternating back and forth. And so that leaves us with a contiguous free space of 606 megabytes, which is plenty for most stuff, but not nearly as much as it should be. And so when you're looking at trying to improve your memory situation, there's a couple things you'd want to be able to do. One is use less memory, and the other is uh, use more of the avail like be able to use more of the available memory. And so in Urbit's road system, you have uh, roads are nested within each other, and so each event, for example, runs in an inner road. So this is all documented in uh, docs/u3.md in the Urbit repo. Um, if you haven't read it, I recommend reading that. A lot of this will make more sense. Um, then right, so each event runs in an inner road, and so it can only use up to 600 megabytes for its computation, even though there should be another 600, there should be 1.2 gig almost of memory available to it. But this is 600 megabytes on the home road, on the outermost road, that is inaccessible within an event. It can be used when you're pulling out the result of the event and putting it in the home road, but it's still basically inaccessible. And so um, something I did the last couple nights was write a compaction algorithm that would sweep through the home road and um, basically take everything and shift it all the way to the left, or all the way to the lowest addresses, um, to remove the free list, basically to make it so that it's not fragmented anymore. And so that's super useful, and it runs pretty fast. It runs in a few seconds, um, maybe 10 seconds. And when I run that, sweep and marked obviously stay the same because that's memory that's actually being used, but the amount in the free list goes down to less than a megabyte, and the contiguous free space goes up to about 1.2 gigs. So this is great. I think this is a really useful tool that we'll get a lot of, yeah, we'll get a lot of use out of. But there's another approach to solving this same problem that is more powerful, which is the old bar pack. So bar pack, what it does is says, okay, well, your state is a noun. So, um, and we have a way of serializing nouns, such that any duplicates are found and deduplicated. And that's jam and queue. That's the way that we serialize whenever we need to serialize. Whenever we send a packet over the network and turn it into a stream of bits, and so we jam it. And on the other side, we queue it to turn it back into a noun. Um, and so you can you can say, okay, the arval kernel is just a noun, and so we're just going to uh, jam that whole thing and then queue it back out, and that should give us a mostly compacted, defragmented space. And the other thing that it does that my compaction algorithm does not do is it'll detect duplicates and merge those to be the same thing. And so it can save a lot of memory that, and so it can actually improve the mark and sweep numbers. Um, and depending on what your particular state is, it can potentially improve them quite a lot. I think a lot of the Ames state, or at least a decent amount of it, is potentially could be improved this way. Um, Regardless, it's a useful function to have, and in general, we should be able to jam large things. We should be able to queue large things. Um, However, it takes forever. For anything very large, like it works fine on a fake Zod that's got 70 megabytes of memory, but it takes forever on something like this, on a more real type ship, which is the time when you'd want to use it. And so what what doesn't make sense to me is why would it take so long? Um, like the compaction algorithm, even bar mass, traces through your entire loom and then sweeps through your entire loom. So it touches uh, every item, every box in the loom, every cell, every atom in your loom, and changes it. In the case of bar mass, changes it several times, um, and then like and then unchanges it, puts it back, and that takes like a couple of seconds. Um, it's fast enough that I think we run it every time we boot, which is a lot. And so what like what that means is that any normal algorithm should be able to do any as long as it's a relatively small amount of things, if it's linear in the size of the loom's just not that big. We should be able to do everything pretty fast. But pack takes potentially hours, um, which is 10,000 times as long as it should, at least. Um, I'd have to multiply it out, but like it takes a long time. And so the question is, what's it doing? And it's very tempting to be like, oh, maybe it's doing this, that, or the other. But that's a useless way to look at performance problems like this. What you actually want is a data-driven approach, which means just attach a debugger. You can do this with printfs to some extent, but like GDB is an excellent debugger. If you're on Mac, I'm sorry, LLDB really, really sucks. I am running on a Mac right now, but I'm SSH'd into, moshed into a Linux server, which is why all the tmux stuff at the bottom looks real confusing. Um, and so I get to like actually use GDB. Now that Urbit is fast on Linux, this is a reasonable approach. Okay. So my basic strategy is going to be run bar pack, attach a debugger, see what it's doing, detach, reattach a few times, and yeah, see what happens. Um, so let's see. Oh, it's working on bar. All right, sorry, I started bar pack earlier, so it's working on it. So let's uh, get a shell that we can use. Find the process number. One of them is the real wick dev. Let me shut down the real wick dev real quick so that I use the right one. Okay. So let's attach to 19427. I need to be root. Okay. These colors are real hard to read. So what is it? Set style off. Now show set style. Okay, help set style enabled off. Okay, cool. I like the colors, but they're just hard to read on a black background. I should play with them at some point. Okay, so let's see where we're at. I wish zooming in worked. I need to figure out my tmux session, like setup better to make that work, but it doesn't. Oh well. Okay, so we can see where we're in. We're not in that deep. There's only 42 frames. Right, so we're in song X inside of U3R sing, inside chbuck add, inside chnode add, inside U3R sing, and so okay. So starting from the top, from frame 42, working our way up. Sorry, I don't have too much set up for Vim keys, so I have to use arrows, which is confusing me. This is all just saying we're running an event, and then we're like, okay, we're in worker pack. Okay, so now we're packing. We go to U3M rock stay, which is what starts the pack, and then we're like, okay, jam. That's what we expect to be in, right? Jam's probably the slow part. First part of jam is jam met. Jam met is measuring how long the jam file is going to be, because if it's too long, then we actually don't support that right now. If the bit index is more than 32 bits, I believe is the rule, which means that you get 29, 2 to the 29 bytes, 512 megabytes. It's either that or 256. One of those two. And so we haven't even actually started trying to jam. We're just measuring to see if it's going to end up being too big. That's concerning, considering that it was running for a few minutes at least. It's in walk 4, so that means it's walking through a noun, measuring the size of a cell. U3H get means that it is looking up a hash table entry, and then it's in U3R sing, which is equality checking, specifically in song X cape. You see various things are optimized out. I should build it without optimization to get more information, but the important stuff's here already. So it's in song X cape, which is probably very relevant. That's a helper function for U3R sing, so it's a equality checking. It uses song X, which is there at number 22. In most cases, if it's having to do a deep equality check, then it uses song X cape. The fact that it has to do a deep equality check is a little bit worrying, but it happens sometimes. So a deep equality check is basically if two things are actually equal and they're big nouns, then you have to go and like actually check that each branch is exactly equal by tracing both of them. Um, if they're not equal, you probably don't have to do that because we keep on each noun a lazily generated mug hash. And if the mug doesn't match, then it's not the same. Problem is that the mug hash is only 31 bits long, and so if and it's not a cryptographic hash, and so if it does match, um, that doesn't necessarily mean that it's the same. It means now you need to like actually check. Um, anyways, so we're in song X cape. We're in here um, putting an item into a hash table. And inside of that, this is all part of putting an item into a hash table, we are checking equality again, which is in song X. So this is this is a little bit to keep track of, right? Is that the main things are like there's I believe 3 nested equality checks, maybe 2. So U3H get, let me make sure that U3H get is what I believe it to be. Um, read from hash table, yeah. Okay. So then U3H get, so we're trying to get something from a hash table. As part of getting from the hash table, we're checking for equality of 2 items. This one is a pathological check for equality. In the middle of doing it, we're putting an item in another hash table. It's a different hash table, I mean, surely, right? Because this is but we can make sure. Um, right, we're putting an item in this one, 1821, whereas the one that we're getting out has been helpfully optimized out. I'm sure I can find it. I'll rerun this without optimizations at some point. But like it has to be different because one's from Jam Met and one's from U3R sing, and I don't think they share hash tables at all, but we'll look at that. And so within this one, we're putting an item. And then it's like, okay, in this, we're checking for equality as well. So I want to go make sure that I understand what's here before I even really look around at what's in the trace. So we have, I don't have tab completion set up because I'm using a local vim to refer to a file that's over SCP. But anyways, U3R sing, sorry, U3, let's start from the outside. We started with U3, whatever jam came from. That was in U3S, if I remember right. Yeah, U3S jam file. So U3M rock stay, but that just calls U3S jam file, U3S jam met. So U3S is going to be in noun serial. So we end up in, well, we can look at jam just says, sorry, jam file just says, so jam file says jam into a file descriptor. Okay, and so we just start by measuring. We don't do anything really before that other than open the file. Okay, and so we're like U3S jam met, U3S jam met. So we start by creating two hash tables, and then we walk through A, which is the noun that we're going to jam, calling this function if it's an atom and this function if it's a cell. All nouns are atoms or cells, so that's all of them. And then we end up freeing one of the hash tables and returning the other one through this out parameter. Okay. And so it said we were in CSJam met cell, so we were looking at a cell. First thing we do is check and see if meta harp. So the harp is that hash table. We check and see if that has this noun in it directly. Now, right. And this is the one I assume that is the problem, or that we're in. I mean, this is just one trace, but yeah, they're at number 25. And so specifically in there, we're in ch node git. So ch node git gets called from u3h git, of course. So u3h git, you give it a hash table and a key, and it looks up. So it mugs the key, uses that to decide which slot it should go in, looks in that slot. If that slot is null, then there's nothing in that slot, so it's not in the hash table. If that slot is a noun, so the thing to remember here is using include noun hash table dot h this. So the possibilities for each slot is it's either empty or it's a noun, in which case it's 2 or 3, uh, or it's a table. So there's, so unless there's very few items in it, it's going to be a table. So if it were a noun, we would do this, but in our case, it's not. It's a node, and so we start looking in there, and so it's like, okay, ch node get. We're looking in this slot, and let's see, what's the next item in the story is hash table 562. We call u3r sing. So this u3r sing, where we say, okay, so we've dug down until we got to a slot which is a noun, and now we say, okay, we know it's a noun. We want to see, is it the one that we're looking for? And that's expensive, apparently. Apparently. The reason we're doing this is that if it isn't what we're looking for, then we just produce that, right? But we produce the value at that entry. Um, but that seems to be potentially expensive. Obviously, we should run it without without optimization to make sure that and take several samples to see if it's actually in this every time. But this is our best guess on a sample size of 1. In particular, that's the one that ends up going to Song Cape, right? So that's the one that ends up being an expensive equality check. Okay. I think it's best before digging deeper into it to make sure we have all the debug data we can get. So let me see where I'm at. I am on not the right branch. Gonna check out IPC Redux which is not released yet, but it's PR'd and it's just nicer to work with. Okay, so then I'm inside a Nick shell, by the way, which is why I can just might even yeah why I can just run configure and make and get incremental what do you call them? Incremental compilation. You can't do that if you're outside the Nick shell and just calling make from the Urbit root directory. Um, that can be a useful way to do it if you're not doing much compiling, but in general, going to Nick shell is much more useful. These warnings are all just saying that something Fortify source really wants you to compile with optimization. I don't know what it is, but it hasn't caused an issue before. I'd love to silence it. Bet you I can. WCPP. I wonder. I forget the. Is it that? I don't remember the. No. Don't remember how you silence it. Doesn't matter. Unfortunately, I think I killed the cache, but we built it, and so it doesn't really need to be made again. But I may as well go ahead and start it making while I use the one that was made. Okay. So let's go in here and detach, kill this, and then instead of using this, we want to use Urbit package, Urbit build Urbit, because that's where make puts it. L, mount, scratch. Yeah, hep L is very important because I don't want to obliterate my existing wick dev. Okay. So let me run that. Since I ran bar pack before, it should start to try and pack as soon as it boots up. Um, I'll give that a little bit of time to get into a steady state. It's the worker I need. So let's attach. Also, something that's useful if it's not already set, I forget, is this. You don't want to stop on zigzag faults if you're actually, what do you say? If you're not, like, if you're running it instead of attaching and reattaching, detaching and reattaching. Okay, so we stopped it somewhere. Um, it looks kind of like we got less information than before. Maybe I attached to the wrong binary. Dash 23489. It's not finding the debug symbols. So I don't mean to quit that. I mean to detach, try this again because that had just been remade. So let's try that. I need to read what these errors are saying. Reading symbols, no debugging symbols. I almost suspect that I just need to quit. Oops. Yeah, no, that's right. And come back. Forget it doesn't save history. Because it was a different location for the binary before, and I think that might be confusing it. Okay. Well, yeah. Let's see. Attach 23526. There, that looks real. Okay. Yeah, I think it's because I changed the location of the binary, and so it was looking in the wrong place. Okay. This looks real, and it's 43. Last time was 42 frames. It looks like it's generally in kind of the same place, except everything's not optimized out. Um, you can see in there, um, jam, around 30, you have, oops, you have jam met, you have u3h get, you have u3i sing. Um, and so we're going to want to remember this number and see if it's the same when we detach and reattach and see if it's actually like if it's comparing the same thing for multiple seconds. Um, I can just copy this number over. And this would make because it could be comparing the same thing to something else. Okay, so inside here it probably all looks the same, right? Um, yeah, it's in U3R seeing song X of something. Uh, okay, then let's detach and reattach. And I don't really need to do Yeah, it's the easiest way to do it for right now. We'll give that a few seconds. Remember, it takes about 10 seconds to trace the entire loop. So if it's still trying to compare the same ones by now, something seems fishy. So we are at, yeah, yeah. So you see that? Uh, 3, 4, 1, that's the same A and the same B. So it's trying to compare the same two items. So we clearly put something into this hash table that we shouldn't have put in that hash table, or that we shouldn't have. I mean, yeah, because we end up doing this equality comparison. So we're either, okay, well, one of two things we know is happening. Either it's taking forever to run this equality comparison, um, um, or we're running, like, we're comparing the same two nouns over and over. We can distinguish between those two by, I think, by putting a breakpoint in U3R sing, although it's not a great way to do it because we hit U3R sing later on. Surely GDB has a way to say, I'm going to look this up on another screen. Um, Surely GDB has a way to say, I'm also going to plug in. Um, yeah, surely GDB has a way to say, tell me when this frame returns, which is what we really want to know. Let's see. Finish. Finish does not leave an active breakpoint. Okay, I think literally just break actually does this. I can test this by doing it near the top of the stack, right? Uh, so if I go to frame one and say break, continue, we hit that breakpoint. I actually think finish is the right. Actually, is finish a command? Actually, I think it finishes a command. I think break is just finish, but leave a breakpoint there. Yeah, finish is the command we want. Okay, let me delete breakpoints, and go to our backtrace. So we want to see does it ever really reasonably finish um, frame 20? Yeah. Are we calling the same comparison over and over, or is this comparison just taking forever? So we go to frame 20. We can try and print out things in here, but that can be exciting because it can be big, basically. Although it is worth just, okay, there's kind of a lot of things that we could print, but maybe there's something useful in there. That's exciting. Um, okay, so we just want to finish this frame, right? So finish. Let's see if that ever finishes. Certainly taking longer than any equality comparison should reasonably take. Because, well, I don't know. It's hard to say what's the correct asymptotics for an equality comparison. Because like we don't have cycles, but it's not a tree, right? It's a directed acyclic graph, which means that you could refer to the same pointer in several places, and you would want to like, and that implicitly, that implies rather a large equality comparison. Um, but surely there's a faster way than this right here. So let's Control C should give us a stack trace still. Um, okay, then let's see where we're at. We're in basically the same place, uh, except that we're trying to finish. Let's see. Yeah, so there's that same U3R sing right there. The fact that it is just these particular atoms, or sorry, nouns, means that it's potentially useful to try and investigate what those nouns are. I wonder what those arguments of song X are because they look suspicious. Specifically, they look like the number of packets in an OTA to someone who has not received any OTAs. If so, then that would suggest something about what these nouns are. But I don't know what A and B and song X are. I would have thought they'd be nouns or something. Um, Let me take a quick look at what that is. So song X is here. Yeah, they're supposed to be just nouns. That's super weird. Oh, it's a little less weird than it looks because, right, so song X is built like many things, like many functions. It tends to build a stack because you do this big giant comparison, and if you then see, you end up with a gazillion stack frames. Um, Notably, mass and the compaction algorithm um, do not blow the stack, even though they trace the entire kernel. Um, so anything that does is, to me, a little bit suspicious. But okay, so because of that, we use um, an explicit heap allocated stack, and so the way that works is we end up overwriting A and B. So A and B happen to be the two specific things that we're looking at right now. And so, or rather, yeah, it's what we're looking at right now. But in this case, um, we go from song X to song X cape, which means that this is what we were looking at. Like that's the equality that we were like, yep, those look equal, so I need to look deeper. When we switched over to song X cape, so song X cape, um, so okay, so there's this over S variable, which is a short int, which would be 16 bits. And so it starts at 0. We increment it every time that we run through this main loop. And if we ever get back to 0, that's because we did 65,000 comparisons. And so we're like, okay, we must be in a pathological case. And so we should um, make a new hash table, call in a songx cape, free the hash table, and then return the answer. So that 97,723 is just whatever we happen to be comparing when we got to 65,000 comparisons. But it's also interesting because I don't know, that number seems really suspicious. Um, I really do think that we were trying to send an OTA to two separate people, ended up generating identical nouns in Ames, and now we're trying to compare those, and it's taking forever. Okay, so then we end up in song X cape, and we're in U3H put. Now what I want to know is song X cape, are we stuck there, or is that like making progress? My guess is that song X cape is making progress. Um, let's see. So I don't know on Emacs keys how to search. Surely there's a way to easily just let me just set keys to Vim. It's, it's like set Vim. Right. Okay. It's set window option G mode keys VI. Okay. Okay. Much better. Uh, so then song X cape. So the first item had the arguments look like that. The second one had look like that. Okay, I confused myself. Read that again. So the, this one, look at fam there. Fam is AAE 40. This is the second one. It's at BB68. I don't know if the third was actually separate, but like it looks to me like it is iterating through songx cape. Um, we can verify this with the finish command, I believe, as well. Um, whereby, so I don't think it's finishing songx cape, but I think it's finishing the thing inside it, right? So if we go to frame 21, we can see where we're at. And so if we just do next, actually, that should check and see if U3H put finishes, right? Um, no, next goes, yeah, okay. Next operates on the lowest frame, I think. Yeah. Okay, so go to frame 21 and actually go to frame 20 and see if that finishes, right? Frame 20, finish. Supposedly that went really fast. Yeah, so now our stack trace is only 22 lines long because that went really fast. And so now um, we're at line 380, and so we can just do next, next. We go back to, this is back to the top of, we should take a quick look at song X cape, which is built similar to song X in that it uses an explicit stack. So while Don is not able to fam, is saying, well, we haven't run out of our stack, right? We haven't popped our stack back to empty. Um, we go through the different things that we can do. And so, yeah, we're back on our next iteration of song X cape. Sorry. Um, and so, okay. And so we go through there, we get to our switch, we end up at 354, which is song head. That means we're working on the head uh, of a cell. The way we work on a head of a cell is we go through to here, we do U3A wed, what does U3A wed do? It's not what's taking a long time, but it's worth taking a little look. Noun allocate. You can always tell which function it's, or which file it's in by the fact that it's like U3A means noun allocate. You can usually use tab completion to make it easy because so each file starts with a different letter. U3, whatever that letter is whatever the file is. So U3A, what am I looking for? U3A wed unifies noun references. So we've verified somehow that these are the same, I guess. And this is saying um, try to unify these noun references. So we do unifying equality, which means that if two things, if we check whether two things are equal and it turns out that they are equal, then we take whatever the pointer was to the second and just point it at the first and decrement the ref counter of the second. If that was the last pointer to the second one, then we can free that. Now, it's important to note that it's unifying, but it unifies on a pointer level. And so just because we tested the two things are equal doesn't mean that we can free one of them. It just means because we don't know everyone is pointing to that to that copy of it. If we had a way to point back, then or if we went and traced and found all the pointers to it, we could rewrite all of those. Um, and honestly, for something like this, that might be worth it. Like given that, at least in some circumstances, you could do something like if it takes me more than 100,000 iterations to check whether they're equal, it's worth pausing, tracing, finding the pointers, and rewriting them. Um, but I don't know, that's an expensive operation. But it's expensive in the sense of like a few seconds. Um, this ends up just calling CA wed who, which is going to do the actual unification, but not that important because this isn't the slow part basically. But it's possible that it's not unifying where it needs to be, so it's worth keeping an eye on. And so okay, so we're back in. Let me close out of these. There's no need for these to be up. Okay. Right. So we go through here, and then we say, okay, we process the head, so now we got to process the tail. So that's like that. Satya is saying, Satya is the state, and so it's saying basically call this function in in an explicit stack way, and then EQ push is saying put that item on the stack, and then we go back to the top. And we say, okay, well now we just pushed on tail, so we probably are going to end up. Maybe I'm misremembering how this works. Or maybe tail is the first one. No, tail's not the first one. So we ended up here. I'm a little surprised. Feels like it's a little bit less stack-like and more queue-like than I thought. It doesn't actually matter here, but I would have expected to go straight into song tail. Yeah, I feel like it does do it like a queue. Kind of weird, but not a problem as far as I'm aware. It's interesting. Okay, so song none means we're working on a noun that we don't know what it is. Um, and so first we check, is it pointer equal? If it's pointer equal, then it's the same thing. Um, if Otherwise, if it's a noun, we check that. I wouldn't be shocked if song Adam took longer than you'd expect. But it can't take forever, right? Because it's just going to be, if it's direct Adam, it's just, well, if direct Adam would have been caught here, so it must be an indirect Adam. Um, if it's direct Adam and equal, it would have been caught here. If it's an indirect Adam, then we just check it byte-wise or word-wise or whatever, and that can't take that much time. Um, if That's checking if A is an atom, then we do that. If A is not an atom, but B is an atom, obviously not the same. If they're both not an atom, then they're both cells. And so we get literal pointers to them, check their mugs. If they both have mugs written in there, and their mugs are not equal, then they're definitely not equal. I'm a little bit surprised that it doesn't generate the mugs. That doesn't call U3R mug. U3R mug is like a memoized version of mug. But my guess is these things are actually going to be equal. If they were not equal, then generating the mugs would be useful. It's worth keeping an eye on. Um, yeah, interesting. Uh, but okay, uh, we can in this one look and see if it has mugs when we get to that part, assuming that they're both cells at this point. Uh, if the mugs are, if we can't tell that they're not equal by the mug, then we're going to end up in here, and in particular, isn't this where the yeah, so it's going to be this that's going to be the slow part, and so what we're doing is we're looking up in a hash table um, the pointer to A and the pointer to B, or the offset, I guess, of A and B, because we don't want to put A and B actually in the hash tables, right? Because those because if you put those in the hash table, then to check whether something's in the hash table, you end up having to check whether those nouns are equal, which is exactly the comparison you're trying to avoid, because checking whether nouns are equal can be expensive, but checking whether offsets are equal is not. It's just a literal compare these two words. Um, an offset is basically a pointer. It's a if you add loon base to it, then it's a pointer. U3A2 pointer is just U3A2 off, add add loon base. If you're following along in U3.imd, U3 2 off just zeroes out the first uh, bit, maybe 2 bits of the pointer. I think it's first 2 bits. I don't know. Doesn't matter. Um, okay, so got is U3H get, and that's going to be the slow part, presumably. Let's step through and see if we actually get to that. Although slow part's not quite correct, right? It actually completed very quickly, but it's the part that it always ends up in, one reason or another. Like at a high level, that particular U3H get goes fast, and what's concerning is the fact that song escape has to run through this whole while loop a gazillion times, is what appears to be the issue. And so we should walk through and make sure it works kind of how we expect it and take a look at things as we do. Um, right, so A is not an atom, B is not an atom. Yeah, because we end up at 328, which is here. So these end up both being cells. Um, really curious what A and B are. I mean, I can print them as nouns easily, but yeah. So we go through and we say, okay, yeah, what is a mugwa? Mugwa. Right. So that does have a mug, and this also has a mug. Um, but the mugs are the same, which means that we're going to have to, which means they're probably identical, but that probably is, true only to, up to 1 in 4 billion times, or 31 bit, I think, so 1 in 2 billion times. It will not be true, which is not very common, but it's like, it definitely happens, right? Um, like that's like well in the realm of like mug collisions happen. Um, okay, especially because it's sort of a birthday problem. Um, or it can be depending on the context. So, right, so we're gonna have to go in here and be like, okay, that steps around in a weird way from my perspective, but we end up at 338, and so we're like, okay, U3NC to off. Um, right, so we're going to construct something out of this and go for it. At this point, what I want to do is start seeing what's in A, B, and harp. Harp is the hash table that we use, the hash table of pointers that we've already compared, basically. It's also a little bit interesting to me that we we make a cell out of these, but cells are ordered, right? So if we later find this as B and then A, we won't find that. But if they're identical, they're probably not like pointing into each other, so it's probably fine. They should show up in the same order each time, probably. But that's another thing to put a pin in and think about. Um, okay, so then, yeah, let's take a look at what's in. You guys gotta be careful printing stuff out because it can be like huge. First, let me take a quick look in the hash table, see how big that actually is, because there are straightforward ways to look up the size of a hash table. Um, I have an example of it. Oops. Um, in Jets, Jam is an E. I think so. Yeah. Hash table size is. Let's just use what? Okay, so I should be able to just do this. Harpa is a. Do I have Hara? So harp is a U3P, which is a U3 post, which means that it's an offset basically, and so I need to add loom base to that to get the to get an actual pointer to it. Uh, there's macros for this, but unfortunately they don't get compiled in. I really should make functions for them as well, just for debugging, or else find a way to compile the macros in. Although that's impossible in LLDB, but I think it is possible in GDB. Anyways, in the meantime, I have somewhere. Uh, see if I can find it. A magic command uh, to do this in GDB. Yeah, okay. So it's going to need to be a variation on this, except that in this case, it is a U3H root, but it's just called harp. So this right here is U3A to off, is uh, this bit mask, or this, yeah. And then the adding two followed by 7 zeros is the adding into loom base. So that's U3A into is a version of that. There's various other macros that mean that. Okay, so this is our hash table. Interesting stuff is max was 0. That means that this is an uncapped hash table. Use was 78,000, which means that we have 78,000 entries in this hash table. My guess is that if we continue for a while, we'll end up with a lot more entries in that hash table. ARM is those three items are used for the clock algorithm, okay, so if you have a Maxwell set, if you have a cap set, then we use clock algorithm for cache invalidation. It's a real simple way to do something that kind of approximates least recently used. Um, and that's all null essentially because it's not capped, so we're not ever invoking it. And so then there's our slots in it. The interesting thing here is that there's 78,000 items in it. Seems like a lot, but it's not like a gazillion, right? Considering that there's 100,000 packets in an OTA, maybe 78,000 is not surprising. If that number gets above 78,000, then potentially it's surprising. So I wonder if we're best off just saying, okay, let's should really put a counter in U3R or like in Sonic Escape and see how many times it is actually going through this. I don't think there's any smoothing that exists, but I should just put a static, or not even a static, just a regular counter here. But okay, let's see what's in A, right? So A is this. Scared to print A. What do I want to do? I want to do U3A is what I want to do is like check whether it's a cell, basically. I actually can see that it's a cell because it has the high bit set, right? The high couple bits set. So if I, or, okay, what would it be? 80. Okay, so the fact that that's set, actually, I even just better way to do it is this. Yeah. So the high bit is set, and so that means that it is a pointer. The fact that that's a 3 means that that it's pretty sure that means that it's a cell and not a direct atom. Sorry, an indirect atom. An indirect atom, I believe, would be a 2, as in the high bit set, but the second high bit is not set. And so because it's a cell, I can look at the head of that, right? This is axis 3 of A, and check what that is. Now that appears to be a indirect atom. So let's try and measure that. I think met is a wait, no, met is in, whoa, met is in C. Okay. Okay. Yeah, it's in C. Okay, so then the one I'm going to want is U3QC. Wait, I want the one that's not going to screw with the actually, you know where I can see it is include jets. Oh, that's not helpful. Whichever one retains, it's going to be jets c met.c qc. Yeah, u3qc met should give me what I need. Okay, so then u3qc met 3 means I'm measuring in bytes, so the block size of 3 of u3x at a. And so this should give me the size of the head of this cell. These 3's are, one's an axis, one's a block size. It's kind of big. Specifically, it is about 100 megabytes, which suggests, so this is probably worth seeing at this point. That's not the one I wanted to open anyways. Although the other one's going to have the same problem, but it's fine. Oh no, I didn't happen to have it open. So in Ames, or more specifically actually in Zeus, read on this fine. Static fragment. I'm nearly positive that this is what it is. So it's a list of static fragments. That's unsent fragments. So we have a message that we have queued up to send to somebody, and we are splitting it into fragments to send to them. And so we have the message number, we have the number of fragments, which is probably going to be 97,000 something or other. We have the fragment number, and then we have the fragment itself, which the fragment itself, I believe, is going to be, yeah, it's just an atom. It's a big atom. And so it's a little strange that this is the head. Oh, sorry, this is the tail. Axis 3 is the tail. If we look at axis 2, that'll probably be the fragment num. My guess is that we're looking at this cell. And so fragment is this one, and fragment num is probably this one. And it's probably going to be a number between 0 and 97,000. The difference between 97,000 and the 100 megabytes that we saw there is that that's actually like 100 decimal megabytes. If I divide that by 1024, that gives you 95, which is about what you'd expect. Okay, so then, right, what happens if we look at the head? Let's just do, yeah. That's a direct atom, and it's 28,956. So that means we're trying to talk to someone, and we have a fragment here that's fragment number 28,956. And there's the fragment itself. So we used to fragment and like actually have the packets there, the 1 kilobyte packets, but that turned out to be really expensive memory-wise because you'd fragment these things and none of it would be structurally shared and it'd be a real pain. And so now we like the fragment for each of these static fragments is actually the same. It's just the whole thing. And then when we're at the moment of sending it, that's when we cut it to be to cut out a slice that we of the data we want, which is just going to be fragment number times 1 kilobyte basically, and then start from there, go forward 1 kilobyte, and that's your fragment. And so these should all be structurally shared, the fragments themselves, which is why we're not spending a bunch of time in song atom. If they weren't structurally shared, it probably would be because you'd be comparing 100 megabytes a gazillion times, as in 100,000 times for each person you're sending this to, roughly 100,000 times. Okay, so then the question is, so we know what A is. What's B? Okay, so B is a cell whose head is 28,956 and whose tail is probably the same thing. It's certainly the same as big, but it's actually worth also just seeing if it's actually pointer equal. I predict that it will be pointer equal, but let's see. So 3a, you can see up there, was exactly the same pointer. Yes, so the pointing at the same thing. So that's why we're not using 100 megabytes times 100,000 of memory, and in particular, actually it would be more than that. Well, okay, so I believe that A and B are being sent to um, different ships, and so because of that, I can actually probably pop the stack and find it, except that it's an explicit stack, so maybe not. But the right, so they're going to different ships, and we may have sent different amounts to each of them. But the problem with this data structure is that um, even if I've sent 100 fragments to this person, and I've sent 1,000 fragments to the other person. Um, there's going to be 900 fragments that are only in one, not the other, and then after that, it's going to be identical. Um, which is not a bad thing, right? The fact that they're identical is actually like a good thing if we knew they were identical, because we could just structurally share the memory. The problem is that I wonder if we could aggressively detect that. Might be able to. That's a possible solution for this particular noun at least, um, and that would save a lot of memory in Ames without having to do significant refactorings. Yeah, that's interesting. When we basically say, because we already scan through in Ames um, for when we put something into no, into unsent fragments, right? Feed packets. We already say um, mm, go feed here. Feed, we already have it. Um, no, this is not the right one. This is where we're reading from unsent fragments. Um, dedupe message is the one. So on memo, when we're going to send something, well, not quite. So well, yeah. So when we realize we're going to send something, so we jam it. Don't really need to jam a message until it's regardless. We say, okay, we're going to dedupe this message by looking at all the other messages. If it's a big message, or if it's more than one packet, we look at all the other um, messages that people are trying to send and see if they are trying to send the same one. And if so, then we use their copy of it. So it's kind of a very direct deduplication, before the duplication even happens. Um, well, I mean, we jammed it, but then we checked immediately. And so what we could do is say, at this point, if we find a list of static fragments, like if they're already trying to send something, and we find a list of static fragments, use that and only build the ones on top of that. But I think that's uh, it's kind of wonky and fragile when what you actually want is that like this data structure is meaningless, right? Message num is the same for the whole list. Num of fragments is just, yeah, it's the same for the whole list. Fragment num, well, okay, sorry, not for the whole list, for each message. Each message, so this list of static fragments might include several messages if your congestion control window is big enough, because it might be like, I can send 10 packets, and the next message the message I'm working on has 3 packets left, and the next message is 5 packets, and the message after that is like 20 packets. And so I'll send the 3 packets from the current message, I'll send 5 packets from the next message, and 2 from the message after that. And so right now, that's a list of 10 items. What that really should be is a list of 3 items saying, I'm working on this message, which has this many total fragments, and here's the fragments that I still need to send. Even if that was just um, a list of fragment numbers, that wouldn't be the worst thing. It could even be a set. We don't need to send the fragments in order. That sounds like a bad idea. But yeah, a list of fragments, or what you could do is say a counter, like a number that says we've sent all the fragments up to this point, or maybe even easier, we've sent, or like they've acknowledged the fragment, like a number that's the latest fragment that they've acknowledged, and then a set of numbers that are before that number that they haven't acknowledged. So the holes that haven't been acknowledged yet. And then fragment is the same for every fragment. This is the only thing that's unique for uh, within a message. And so if you did that, then you've reduced the memory usage a for sending an OTA that's 100 megabytes by a lot. Even though they share even if we assume that the fragment was already being sent to someone else, so we don't count that as memory, it's still uh, this is what 3 cells plus 3 cells times 100,000 is 300,000 cells, which each cell is 6 words, which is kind of a lot, but whatever. So which is 24 bytes, and so it's 300,000 times 24 bytes is uh, like 8-ish megabytes, which isn't that much, but it's like way more than it should be. Um, and because it should be like uh, 6 cells should be like 100 bytes, maybe 200 bytes, not 8 million bytes, right? There's a big difference there. Um, so that's a refactoring that's worth doing. And potentially solve our problem. However, like that's like kind of very worth doing. But even if we have these sort of pathological cases, pack should still work. So I'm interested in why is pack um, tripping so hard over this. Um, I really do want to counter in this cell, but yeah, okay. So you know what A and B are. Let's see what else we can learn. I mean, we can walk over this, see whether it happened to get it for this one. If it did, that's quite interesting. That's super interesting if it did, right? Because if it didn't, it's like, well, maybe we only went through 78,000 and there's 90,000 and that's all there is. But if we have already compared these pointers, which is what it would be the case if we find it in hash table, then that means something's weird, I think. So let's see where we at. I always confuse myself whenever I hit L. So we are at 338, which is how do you L338? Is that how that works? Yeah. Okay. Um, so we generate the key, and then we run u3h get. It should be relatively fast, although it spends most of its time in there. Still, it's like basically instantaneous, which means it must be running a gazillion times if it's spending most of its time in there. Okay, so now got is a big number. Um, I think that's U3 none. Uh, U3 none is in don't remember what U3 none is defined. Okay, grep. I actually want to only C and H files. Okay, U3 none. There's going to be actually a lot of cases of U3 none. Okay, but somewhere should be an include. Let's see, imprison, nouns, aliases. Okay, so it's in noun aliases. I have this open another tab. Oh well. U3 none. Noun, which is not a noun. Okay, so it's 0 except. So if we add 1, it should be 0, right? I think that's what this is. Yeah. Okay, so U3 none. That means that we did not find it in the hash table, which means we get to keep looking. Okay, then we should end up putting this in the hash table, if I'm not mistaken. Although we don't. What? I'm confused. I think I'm misreading this. Yeah, okay, so that's the while. This is the switch. So, once we've determined that two things are equal, we determined that they are equal? Right, so I don't think this works. I don't think we put it in at the right time. Right? Okay, so we generally end the switch statement with either, okay, so, no, sorry, I'm misreading that. So we end the switch table with either break, return, or continue. And so return means we found out that it's not equal. So we return C3N. It's only if we get through all this without returning early that we can say, okay, it must be equal. Break and continue are the interesting ones. So continue says, I don't know whether it's equal yet, so start the loop again. So I probably just push something, or maybe I just pop something, but I don't know whether this is equal. No, sorry. Yeah, basically. Um, and so, and then break says, I do know that these particular things are equal. And so at the point of equal, we say break. If their atoms are equal, then break. Um, Otherwise, like cells are only equal if the contents are equal, and so that's why you don't see any breaks in here, except, well, not exactly, right. So we can know that a cell is equal if we found it in the hash table. And so if we did, then we push some head. Um, the fact that it seems to act like a queue instead of a stack maybe is relevant to this. Let's see. Okay, so we push song head, and then we continue, which should get us up to here and say, okay. But it seems to be kind of intentional. And so it'd be like, okay, let's try and unify U3A wed, and then push song tail, unify the tail, and then break. Break will get us out of that switch statement. We'll then push those into the hash table. Why why does a song head and a song tail like have to be pushed in there? Why don't we just like do it? Like why do they have to be separate functions? They don't recurse. They don't like it. Song head leads inexorably to song tail, right? Um, so and like when we get back up here, nothing interesting happens. Why does it do that? And of course, the danger of not doing that is that like if it doesn't go straight to song head or song tail, then it's not gonna find that they're equal, right? Like I'm gonna put this, they're gonna get stored in the hash table in the wrong order, and so you might miss hash table entries when you shouldn't have. Am I misreading that? Let me see if I can understand what EQ push is doing. So we start with EQ frame, which is defined right there, which is just state, which is song none, song head, or song tail. It's these. C3Y just means it's a byte. Um, you and then it's like A and B. Those are our two stack items. And so then EQ push says we're going to push a new frame. We're going to do that by saying, okay, uh, we take our, so we take fam, set it to song tail. Okay, I'm confusing myself. So what this is saying is, so like what this is saying is, uh, this is going to be the return type, right? Let's say the return location is what it's saying, and then we push a new thing onto the stack. And so what it's saying is after you finish doing, okay, you can push again. So we have um, mauve, which is probably just size of EQ frame, uh, and then so YS means assigned byte, and then off is an offset, probably dawn or some variation of that, and then we have two nouns. So what we're saying is basically we need to compare these two nouns. Right. Okay. So this is saying we found something to do whatever. If we didn't find something, then we need to compare the two nouns, and only if it finishes that. If it finishes that without aborting early with return C3N, then we want to go to song head. Okay. Okay, that makes sense. Because yeah, we can't say like we can't put stuff in the hash table yet because we don't know that they're equal. And so the way this works, right, is it's a little confusing, but fam is a pointer to the topmost stack frame, the stack frame that we're in right now, and so we don't have to pass in fam because fam is also just the top of our current road stack, right? Because so each road has a stack and a heap. We're just at the top of the road stack, which is cap p, and so we say, okay, bump the road stack forward um, by mauve, which is going to be either positive or negative depending on if it's a north or a south road. That's why those are signed offsets. Um, and so it's like, okay, bump that, put a new EQ frame where it just was. Um, we need to compare these two nouns. Like this is the recurse step, right? So we make a new frame that starts with song none, which means we don't know what it is, and um, set A and B, produce that new frame, and so we set that to be our new top frame. Okay, that makes sense. So then we're like, okay, if that ends up finishing, then we want to go to song head and say, we just proved that they're equal. And so we want to go ahead and um, run song head. So, which is going to, sorry, we check whether the head of the first cell, sorry, so A and B are cells, right? We check whether A's head is equal to B's head. If it is, then we unify those inside of A and B, um, because that's the place that we can unify them. Um, and then we check whether A's tail and B's tail are equal. If so, we unify those, and we know that that these cells are equal, and so we can break. Break gets us to here. We say, okay, well then, um, let's go to let's put in the hash table, and then pop it off the stack. Cool, cool. Then make sure I understand what EQ pop is, but I think it's just subtract. Yeah, it's just subtract from cap page. Just be like, okay, we don't need that top frame anymore, so just bounce back. Um, and then we go back to the top of that loop, and we say, okay, uh, let's see what's the next thing to check. So it is depth first. It is operating correctly. Um, okay, that makes sense. So then the question is, how like does this get to be a crazy number of comparisons, or why how do we end up with a gazillion things um, in this cache, like in this hash table? And I mean that's a lot, but it's not. 78,000 not that many, right? uh, do I have that? No. Harp. uh, I'd have to find it. It doesn't matter that much, but this one. Right, 78,000 is a lot, but it's not like a gazillion. Okay, well let's step through this a bit and just. Right, so it turned out to be U3 none. I can't just print U3 none, right, because it's a macro. Yeah. Uh, then it's like, okay, well let's check the head. EQ push, continue. Go back to top. And we're like, okay, well the head, we happen to know that the head, well, that once we set A and B, that the head, yeah, and the tail are just numbers, so they're fine. And so we're going to go in here and be like, okay, well, it's song none. If A equals B, well, they're pointer equal, or in this case, direct atom equal. So we're good, break. And in fact, we then be like, okay, well, that's funny that we'd be like, uh, these things are pointer equal, and so I'm going to put them in the cache. That's super weird. That's totally wrong, right? That can't be cheap. That can't be cheap. To just like put a bunch of atoms that we found are equal into a hash table that we don't need. That's a waste. That's a waste. It's also like trivially fixable, right? Just check and see whether they're direct atoms. Yeah. Let me look at some of those old stack traces back when they were 40 lines and just check and see were we in put, because if we were, like here, for example, we were in hash table 230, which is, that's not, sorry, I meant who called put. So in 378, retrieve 378. So like that sample, for example, we were in put. This one we were in put. Interesting. This one we were in. I mean, regardless, like I mean, it's just trivially easy to not have to put it in there. The problem is that they're just numbers, and they probably do have something in there, and that's a relatively expensive part of it. I doubt that this will just like solve everything, but I'm inclined. I mean, yeah, I'm inclined to just fix that. Um, by saying basically, uh, so we want to unify. Sorry, we want to not have to check again if it's anything but a direct atom, right? The thing is that lots and lots of things are direct atoms. It can't be a majority, so I don't think it's a real problem. But all we have to do is say if, if I remember right, it's U3 du. No, du checks for cell, I think. What I want to say is that's in the that's that was exciting. I moved the tmux pane. Um, include noun retrieve dot h. No, that's just saying, no, that's not what we want. What we want is U3A is cat, which is, yeah, it's just U3A is cat. I remember that one, which is just saying if it's a direct atom, right? So if C3 know that it's a, and we only need to check one because they're equal, then we want to make a key, put it in there. If not, then like no need to do that. Yeah, data makes that big of a difference, but why not? Okay, so uh, so just run it with that and see if anything changes. how to silence that warning. Should be a way to silence it. Regardless. Yeah, I should just run it again. Okay, so detach. Let's kill it. Run again. Attached to 24152. Still in jam met, but we're in Git this time. Not working on the same nouns as last time. I should have hit enter. Dang it. I can find them. Let's see. Let's take this. Yeah. And this. So that's not what we're working on right now. I wonder what we are working on. I didn't give it very long to, or maybe I'm looking at the wrong part. Wait, because we're in U3RC. We're in walk for U3RC. Yeah. Well, let's try letting it go for a little longer. I didn't let it go for real long. Might be working on something else for a little while. Now we're in Song Cape for someone at least. Uh, yeah, but at least it's in Cape. That's nice. Um, Still got 63,000 entries in here. But I don't actually know that. Let's go a little further, see what. I mean, it's interesting to me that it doesn't seem to be dropping into that put nearly as, like, well, either time this time so far. Um, Still new to our seeing, but see, this time happens to be in the unifying equality. But I feel like these numbers are changing, right? Like, I mean, U3S gem met shouldn't be changing, but U3S, I mean, if this number changes, uh, then we're making progress at a level that we definitely weren't before. But also, I don't know, it went on for a little while. I mean, it's pretty deterministic. I would have expected it to get stuck on the same cell. I can make that switch back and see if it gets stuck on the same cell next time. Like that, putting stuff in hash table shouldn't be that expensive. Like it just shouldn't. I mean, now it's measuring an atom. Definitely feels like it's making progress. I mean, nothing I can do, of course, is go to frame 17 and like see how long it takes for that to finish. Like basically immediately, right? This is super interesting. Okay, I'm gonna detach, let it go for a little bit, because like I do expect it to take some time, especially since with no optimizations. Um, hmm. Very interesting. I'm going to step away from the keyboard. I'll be back in a minute. Oh, hey, Bale memed. That's quite interesting. Would have liked to be attached when it was, but like, regardless, I think that's like massive progress, isn't it? I should check that to make sure that it's actually like, I mean, I don't know massive progress, but it's a first step, right? Okay, let me make this easy. I don't know what things are used. I'll use that. Uh, Actually, no, sorry, this is what I'll do. Make it easier. Right, so let me make sure I have this logic right. If it is not a direct atom, then we want to put it in the hash table. But if it is, then like don't bother. And honestly, I really feel like, dang it, I seem to have lost internet. That happens sometimes. I think it's an overheating thing. I can try unplugging my laptop. Um, I need to get an extension cord so that I can plug it on the other side. Uh, but I think the only extension cord that I have here is a 100-foot extension cord in the barn. I'll find something. But this is also why I had to worry about this if I was streaming. Anyways, I'm not streaming, but I also am developing on a foreign server, so only so much I can do. Uh, let's see. So, do I think it would be? This is a ping command, by the way. Do I think that it would potentially take a really long time to put a bunch of atoms in a hash table? I mean, yeah. Hash tables are like I really think our hash tables like get slower the more things you put in them. Which I mean, is gonna be true to some extent, but like, come on. Also, direct atoms don't have mugs, so we have to run mug on each of them. But we're not like the traces were not in mug; they were in sing. But they were, if I remember right, they were in sing of. Okay, it's back. They were in sing of like. Well, no way, I'm thinking of a different part. But like they were in sing of direct atoms, weren't they? Let's see if we can find it. Uh, Actually, we were about to redo it, right? So let's just do the new one, right? There we are. Okay, so then I mean, bail meme can mean several things. It depends on where it got to. It depends if it like finished jam met, for example. Uh, okay, so then let's try running this. That's the most interesting one to note. 24473. If I attach even now, I'm already working on that exact same thing. No, I am working the same thing. I just miscopied those. I just remember that that's what the B is, but the A is definitely the same. You can see. Uh, yeah, so it definitely makes a big difference. Let's see. Uh, so if we look at what's on top of this, for example, we're doing buck add u3r sing. Key is this. Let's look at what's in that key, right? We'll probably just print the key if unless we miss our guess. What am I in? This is ch buck add, and I have a haba, kev, and uswa. So let's look at haba, which since it said like that, so we use a form of Hungarian notation. The u suffix means that it's a pointer to a struct, as opposed to the p suffix, which is a post, which means that you need to add the loom base. Okay, so p haba, I should be able to just look at that directly. Oh, all right, haba is a buck, and it has length 2,374. What? Whoa. What's haba? Um, so this is buck add, right? Buck add. This is a bucket. Don't we linearly search through buckets? Yeah. Wait, seriously? Satwa is then the. Yeah, we're just literally searching through 2,374 items. Dang, that like. The heck? What are those items? Can we see those items? Well, I mean, we can see what's what we're looking for right now, but I mean, yeah, it's U3 down Kev, right? So, uh, can I see what this is? I think this is small enough to U3. I'm pretty, yeah. It's the noun 11766, 11766, 0. Uh, as in, the two things that we were comparing are the two direct atoms that, and we make a cell out of them, and that's our key, and our value is null. Um, what's in this bucket? Let's figure out how hash tables work. If this is the problem, then that's like huge because like that probably blows it wide open, and it tells us like, oh my gosh, if this is the problem, we might solve problems related to the compiler as well. Okay, okay. So the first thing I want to check real quick is we need to get to where this. All right. So if we switch to frame 18, which is the put, do I have a har? Yeah. Okay. So har is going to be the root of this, and it's going to tell us how many items are in it. 9,487. What? And they're like all in one bucket, or mostly all in one bucket? Which bucket? So we end up in chslop put. Well, wait. Sorry, which line were we in? We were in 230. So, uh, First of all, yeah, we are mugging these direct atoms, which is not a cached operation. Apparently, it's still pretty fast because we're not any up in there. But to do that, or sorry, this will be a cached operation because we're mugging the key, which is the cell of those two, and so that's fine. And so we end up in 28, end up in slot 28, which uh, okay. So then, right, so we're in slot put, some add, some, what is some add? Add to node or bucket, which I can see which one it is. Node add is what we're going to do a few times, right? Some add, node add, slot put, some add, node add, slot put. Oops. And then we end up in slot put, some add, buck add, and somehow we end up with a bucket that has a gazillion entries in it. Okay, I gotta see what those entries are. If we end up like, I don't know, adding the same thing multiple times or something, I mean, surely the hash tables won't let you do that. Surely. Uh, okay, so we have to have a. Oh, okay, I also want to see real quick what's in hand the which is here, right? Sorry, frame one. Hanva means it's a void pointer, which I can just cast, but there's actually no need to do that because that's not the right one. Sa ch slot put frame two is probably what I want. Well, nah, frame three. Frame three, I'm gonna look up Hannah, which is a node. Bit masking it. Again, not a lot of information there. Okay, so we're in here. We have a bucket that has 2,374 items in it. We're linearly searching through them. To we're linearly searching through them. Unless I really don't understand what's happening here. Okay, so ch buck add. And so we're like, okay, U3 noun. Okay, yeah, it better be doing U3. So we mutate the bucket. It's super wonky. We actually, we probably, yeah, we reallocate um, the whole bucket. That can't be cheap. Yeah, that really can't be cheap. But uh, and I see why you'd want to reallocate it. So realloc is try to just extend if you can, and realloc is the word aligned, like is the word counted version of that. Um, we do that for a lot of things, like alloc. We have walloc, which is the word version of that, and so on. Actually, sorry, that's the replacement for malloc. Malloc is byte aligned, walloc is word aligned. Anyways, um, there's also size of and wise of. Size of gives you the number of bytes. That's a built-in C. Wise of is one of ours. Okay, chbuck add gives us, so we say, look through everything in Satwa, which is like giant, and say, like, yeah, because it really is just huge. Just to confirm this in my mind because I was having fun with this kind of thing before. If I cast this to a word pointer, then I can I can see that, but I can also then look back and look at its that would be the sorry backwards. That's the ref count, so there's only one thing pointing to this, and this should be the size of the box, and the size of the box is 2,378 words, which is huge, because that means that the box is one word for the size, one word for the ref count, one word for the size at the end, one word for the length there in the middle, one word for satwa, and I feel like we go one word over, but that I'm sure that we don't. Um, yeah, okay. But then what I can do is say, okay, so first of all, let me make sure that this is packed the way I expect it to be, right? Uh, yeah, so a trick that we often use is, I don't know, trick, I actually don't know exactly how standard it is, but we use it like all the time, is if we look at the uh, hash table, and if we look at what a bucket looks like, it's length and then a zero array, or sometimes we write that as just a pointer, like a zero length array. And what we do is when we actually malloc this, this points to the word right after it. Um, and like this is really just the beginning of the bucket, right? And then there's a bunch of like there's like a data section after that. This tells you how long that data section is, and this gives you a pointer to it. Um, it's sort of like I mean, yeah, which points just kind of to itself in a sense. It's weird. Anyways, oh, that's why it's -1. It like it is itself. I don't know. It's wonky. But the point is that it's just packed or like placed at the end of that struct, um, which means that we can just start printing these things out, right? We can say, okay, yeah. So well, yeah. So we can say, okay, one is that. Now, what is like two? Well, two is just going to be a noun. What is three? That's going to be a noun. And then the question is, maybe we can print these out, right? Um, maybe we can. I think that'll cast through fine. Yeah, okay, so that's what's at. Look at that. Look at that. Dang. Okay, that's how you turn something that's like sort of linear into like really, really bad asymptotics. Dang. I don't know how these all ended up um, in the same bucket. That's really, really screwy. But like there's the like like that's probably the eureka moment, right? Like I mean, like the bail meme, we might just actually run out of memory, right? Maybe if I compact that, it'll actually succeed. But like the, at least for whatever the first problem is that like basically by putting in a gazillion of these pairs, and somehow those pairs end up in the same bucket, or at least mostly in the same bucket, and so we linearly search through them. If if you end up with 10,000 items in there, then that means you added them 10,000 times, and the only way you can add something to it is by checking, make sure that it's not already in there. And so the 10,000th one, you had to check 9,999 other things, and that one you had to check 9,998, which is that quadratic or is that worse? Uh, it's quadratic, right? It because like doing it once is linear in the number of times you've done it. And so you do it over and over. Yes, quadratic, which is bad. Your hash tables are supposed to be like constant time or something, not quadratic in the number of things you put in it. Um, yeah, so that's going to make comparing direct atoms like way, 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 way slower than they would be if you just compared them directly. Okay, that's a significant win to recognize that. Now, um, if that's the Eureka moment, there was previously a that's funny moment, which it was um, when it was like, huh, that's weird that we're putting direct atoms in there. Um, but there's also like, these things uh, aren't isolated because there's a bit of a that's funny moment here with of like if we have 9,000 items in this hash table, why are 2,000 of them in one uh, in one place, like in one bucket? That's like that doesn't make any sense. Because whenever you hit that bucket on either a put or a get, it's gonna be really really slow. Um, and like it's not like there isn't a lot of nodes. We went a ways in. I don't super understand how our hash tables work, but like we're at song X Cape, right? And we're like, okay, let's go to a node, which had a node in it, which had a node in it, which had a node in it. It's supposed to go up to 5, right? I assume that's what it did. Yeah. So the left is how many bits left in the mug, and so it's like 25 bits left in the mug, 20 bits left in the mug, 15 bits left in the mug, 10, 5, 0, and then it's like up, nothing more in the mug, so we can't get anything better, right? But it's not that bad of a birthday problem, is it? I mean, it can't be because like to have like a, I mean, like how much would we expect the collision to be? We'd expect the collision to be um, 31 bits, whatever the square root of a couple billion is, right? Square root of a billion should be like 10,000, right? 10,000 times 10,000 would be 100 million, so like 30,000. So we'd expect if you have 30,000 items in there to have an average of one per bucket. And in particular, it should be, I don't know, normally distributed, but pretty close to it, around one per bucket. In which case, this is, a standard deviation of about a gazillion, maybe a few thousand, but which doesn't happen. It was either our mugs are screwy, it's possible, or um, or hash tables are screwy, it's also possible. Regardless, I'm going to write this down as an important finding. Okay. Although I can also just look back at the recording. I can look back at the recording, but it's basically just um, don't put atoms in hash table in song X cape because it's really slow. It looks like there's a bucket in the hash table with 2,700 entries, while the whole hash table has 99,000-ish entries. Um, Notably, the items in that bucket seem to be of the form that. It's super wonky. Okay, so we got to see why it's going in there, right? But fortunately, it's all going to be in this stack frame. Um, this is why debuggers are great. Okay, so we're putting in this. So we look for what our slots are. Also, okay. So we go back into U3H put, which is going to go into CH slot put, right? So 18 frame 18, and this is where we're like, okay, print inkswa is this because print mugwa is this, which just to make sure that's correct. Okay, remwa I think remwa is saying just take the last 25 bits, right? Because we're using the first 25 bits. Let me make sure that I know what cut end does. I think I have this grep up somewhere, right? Oh, it's in here actually. Wait, sorry, that's where it gets called. It is also defined here. So it's okay. Extract that many low bits by saying take the number of items there, shift them to the left by that much, subtract by 1, so you get biwa ones, and then bitmax out on A1. Yeah, that makes sense. Okay, so then, yeah, we're here, and we're like, okay, let's do that. Put this into just slot put. And yeah, I mean, that gives an interesting result. I mean, no. Har Yuzwa goes in there as a as a as a as a pointer, right, as a reference, so that they can increment that if we put in a new one. Okay, okay, that makes sense. So we put in. Okay, so we say slot put. Here's your slot. Here's your key. Here's 25. Here's the remainder of the mugs. So we're not like remaking this mug. Um, okay, so we end up then in just slot put. And so we say, okay, here's these. We're not calling mug anywhere, right? No. We're like, okay, leftwa gives that, and then we say, okay, right shift by leftwa. Uh, so for example, there's 25 left. Now it's like there's only 20 left, and so it's like, okay, right shift by 20, so that gives us the high 5 bits. Okay, so we have the high 5 bits, which should be 64 slots. We cut the low 20 as remwa. I don't know mapways. Um, if bit set mapwa bitwa, what's bitwa? Uh, so that's saying basically if there's something in this slot, then put it in the slot. If there was nothing in this slot, then we gotta like make a slot and stuff. But presumably in this case, there's like stuff in the slot because there's stuff in the bucket way down there. Um, I mean, surely, right? So after Chino to add, we should end up at just slot put to make sure that's correct. where do we get? Okay, so node add slot put, and specifically it's the one that's at hash table 109, right? Right. So we end up in that because of course we have something in this node. Um, I mean that sounds reasonable. So we end up back in slot put. Actually, I don't think we've hit slot put before. Uh, okay, so store key value pair in a slot, and so we say, okay, if it's null, so what is u3h now be warm? So we put some u3h now be warm is saying, oh right, it's this thing, right? It's saying that we put in a fresh entry, so we mark it, we mark the two high bits. It's weird. Um, and we just put it directly in there, right? If there wasn't a slot here before, then we just put it directly there. We don't want to have to indirect 5 times. And so we're like, okay, cool. But presumably in our case, there was something there, and it's not a noun. Uh, I think we were at 206. That sound right? Yeah. So slot put. Yeah. So maybe 206. Wait. U3H put went directly into slot put, but I haven't seen the slot put before. Did I just go to the wrong one, or am I? Did I forget what I saw just a second ago? Oh yeah, I ended up tracing the wrong one. Okay. I mean, nothing interesting came out of that, so it actually went straight into just slot put. And so we're like, okay, but there is something, and so we go to some add from hash table 206, which is going to end up in node add, but we don't trace these one at a time. Some add, we just give it the slot and the arguments we passed in, and then we're like, okay, well, we're either at the end, which we're not yet, not until the end, in which case we debug add, or we're here, in which case um, we want to node add after casting to a Hannah. And so we're like, okay, Hannah, and we should have use what here, right? Which should be printable. Let's see. Uh, so this is, we just got into like frame 15, right? And use what is a pointer, frame 15, 9487, that's how many things are used total. Okay, so then we're like, cool. We do what this is what I traced through before. Dig into it, we end up with just slot put, go back and forth between those a few times. And while we're doing that, remwa should be getting smaller, right? Remwa, whoa. So remwa here is 10 million, and then it goes down to 82,000, and then it goes down to 8,000, then it goes down to 58. It's a little hard to see. Node add is where the nodes happen, right? So if I'm really fancy, I can use both tmuxes so I can leave it. They're both in copy mode. That's not going to mess me up. Okay. Right. So when this drops to right, so 8250 to 58. Right. So each one of these corresponds to an actual drop. It's not like we zeroed out too early. But then we end up with remwa ends up being 0, right? But only when left was 0. Yeah, I mean, like, right, it's only when we got to the last bucket. And in that case, we don't go into just slot put. We go into we do go into just slot put. What's Chnodad trying to do? Wait, which one is supposed to be? Just some ad is the one that would choose, right? And so we get here, and we're like, okay, just some ad. Uh, Left was 5, and so then it's just some ad. Left was 0, and so we're like, okay, in that case, it's weird though because by the time we get into Chnodad, left was 0, and rem was 0. Doesn't make any sense. Do we edit this in place or something? Maybe. Oh yeah, we're editing this in place. I think that's what's screwing with me. That's why it's going down a little faster than I expected. Right, right, because yeah. So left was 0 because we already subtracted 5 off it. That's okay. Remwa has a similar pattern, right? Yeah, but of course it gets passed by by value after that because it's C. Um, that's why it ends up going all the way to 0 for that reason because we shifted 5 bits. Uh, so it's in bucket 26. Here it's in bucket like 2. Or sorry, slot 2. Right. Okay. So we end up here. So that makes sense. Now that I understand what this hash table is doing, the question is why is it putting them all in the same place? Uh, and that's going to be either that they're all generating like similar mugs, which would be really screwy, or I don't know, I can try to see if they generate similar mugs because I have these things right here at frame 0, right? So what was I printing out? These ones, right? Oops. Because I think it should just be like just call U3R mug of that, right? And so U3R mug of actually sorry, it is gonna be U3 noun pointer of this. It's kind of wonky that way. Uh, so U3 noun is a U3W under the hood. So this is going to count at the same place. Okay, so that's that. That's that. Look at that. Okay, that's a problem, to say the least. Um, um, Dang. Okay, yeah, that's definitely a problem. Oh man, there is a mug bug, but I don't think it's related to this. I don't know. Maybe it is. That's crazy because these are definitely not the same thing, right? But they mugged the same thing, which once is you should go to the lottery. Twice you should check for bugs. Uh, okay, so U3M pretty. I can just call that on the same thing, right? Okay, that's it. Oh man. Okay, so this is something that we can just try and like a ship, right? Um, I can go here and open up WikDev. Uh, Hopefully nobody's, telling me secrets right now. Um, I shut it down, so I actually, what I'm gonna do is can open it in localhost mode so that I don't end up having to download a bunch of stuff. Let's see. This is the real WikDev, um, and I'm gonna try and like mug those nouns. My guess is that I don't know, maybe we overwrote those mugs, or I mean, I have no idea. But wow. Okay. Uh, so 11.756, 11.756, 0. That's a reasonable noun. Now let's mug it. Okay. What the hell? What the hell? Is this the mug bug? What's the mug bug? Oh man. There's a it's on some branch, the fixes, right? But there's like a pull request for it, I think. Yeah, 'cause there was a pull request that got merged for it actually, and then we had to pull it out. U3 clear cache mugs on cell edit. That can't be what's happening, right? Because I mean, surely we're not editing anything, right? We're just making new ones. Huh. This is super, super weird. What, like, what? While I try and digest this, like, on the one hand, this is a really disturbing bug. On the other hand, um, dang. On the other hand, it is interesting that, like, the way you find this bug is just like, what's it doing? Oh, it's taking a long time. Let's look through the backtrace, read the code, and like print stuff out. And this is all like our code, right? I didn't even know how to test this. I mean, like, or like, I mean, I can just look through what mug is doing, but like, okay, what does that look like as binary? That would be interesting to know first. Kind of nondescript. Aren't mugs supposed to be 31 bits? Oh, this is 31 bits. Yeah. Uh, like, I mean, how free can I be with this, right? Is everything the same? Is there only one mug? What the heck? That's a different mug. But of course, and that's a different mug. Oh, because these are not the same. But if they're the same, what? I mean, like, what the hell? I mean, can we make this simpler, right? What? Did I type something? Okay, there. Um, can we get rid of this? Is Mug just giving us a structure? What? I mean, this explains why our hash tables are so incredibly slow. Oh man, that is incredibly broken. Oh man. I mean, teachable moment, right? Like, this is why even when you're like, oh man, I made U3R sing so much faster by not putting direct atoms in the hash. You're like, ah, that like might have wide-ranging implications. Um, but like you keep digging. You don't just be like, ah, my job is done for today. I made good progress because oh man, oh man, oh man, this is bad. Oh man. I mean, Muggs being that screwed up. Oh man, what the hell? That's all our sets are probably hugely unbalanced. Oh man, what the hell? Uh, I mean, okay, I gotta keep digging to figure out why, but like, this is good enough to at least like, post on chat. Like, um, oh gosh, uh, man, that's just, oh man, man, man. I don't even know how to get. Oh man, like people look at Mug. I mean, there's this. What the heck is happening in Mug? Oh man. Okay. Uh, that's a U3R Mug, right? Well, presumably. Yeah. No, that one's looking at U3R Mug. So U3R Mug, which is going to be this. Give us a little more looking room. We're gonna want to step through this probably, but like, okay, so I mean, how far does this go, right? Like, if do they have to be both direct atoms? What if they're indirect atoms? What if they're cells? Okay. Ah, man. Okay. Let me try. Oh, the Mac's gonna die. There we are. Sorry, I meant to leave that one there and take this back here. Right, so like, what about mug 00? Yeah, but 000 and 111. Those are different. Although I'm nearly positive I saw that 343900 number earlier. Didn't we? We saw that, right? And the mug 00 when we saw that. What the heck? Specifically, what the hell? This is so screwed up. Okay, you threw noun verb. So we'd be like, okay, you three are mug words. If it's a cat, then we do that. But this isn't a cat. So let me get a, so we can get a terminal here. Probably a fixed audio area. Cool. Okay. Make sure I can duplicate the result here. Yeah. Okay. Uh, I mean, mug is jetted, but like met is not, right? Or okay, what we need to do is see whether this is just a problem with mug or a problem with the jet for mug. Okay, so mug is jetted, but if I copy this out, got what is it built out of? It's built out of muck. It might be jetted, but it might not. It is. Yeah, so it could be anywhere in here. But surely based on like the height, I mean, no, it's got to be in here though, right? Because Murmur 3 takes an atom, and that's not what we're into, I think. I mean, what? Well, I mean, the jet thing is running. I can step through the jet. So we have okay. Okay, I mean the reason why that would produce the same as this, so that's not going to produce the same thing, but this will, on account of because the head produces the same thing, so of course the whole thing is going to produce the same thing. Okay, so specifically, the only like base case that we've identified is a cell with identical heads and tail, like head and tail. So like, okay, Mab is not a cat. It's not a direct atom. Check and see if it's been mugged. There's a chance that it's already been mugged for whatever reason. Be wonky. No, there's not a direct atom, and so it is a pointer into loom, and so assuming that it hasn't been mugged already, which is surely what we're getting to, then else if U3A is atom, but if it's not, then it's a cell, in which case we push mughead cell 0. What is 0? Okay, like this is the same pattern as we saw for some cape, right? So we just see what a mug frame is, which is a tagya, which is the state or whatever, and then cell, and then mug. So that's what we think the mug is so far. So we start with 0, and then we'd be saying cell mug head. Okay, so we're like, and then, but we push. So we say, okay, but we didn't change our. Actually, don't know what tag is. Mug head appears to be an option for that. Okay, so we get there. We go to advance, right? And so we're like, okay, advance because we pushed. This works significantly different than song X cape. So we have our mug frame. Okay, so what does pushing mean? Uh, pushing means we just shift forward and right, okay, and then mark it in tag ESL and mugwa, and so then we're like, okay, so we put that onto right, so we advance that. Okay, and so then we're like, that becomes cell head, and then we're like, okay, let's go to. So we know what Veb is. We find out that its user is cat, which, I mean, should check. Those are different. Presumably that's giving us a different number. We'll step through this in the debugger at some point. And so then we retreat, which is to say we mug pop, which is just going to be stepping back. And then we say, okay, we say, okay, cool, cool, cool. Let's take mug push. So we were at mug head, and so we're like, okay, mug was the mug of the head of Sella. Really? Doesn't sound right. No, actually, probably does sound right because we took mugwa, wrote it into that. All right, so mugwa is our return register, right? And so it's like mugwa push the stack frame to mark tail recursion, record the mug of the head, and read the tail. So push mug tail mugwa web is now fama.sella tell. Right, so we're like, okay, this is mugwa. We're gonna record it in our stack. Push mug head. Sorry, push a mug tail. Advance into the mug tail. This is the way I thought song cape worked, and realized it didn't. And so we're like, okay, now we have a song tail, and so we advance on the tail. We get this. We're like, okay, that's what it is. And so then we're like, okay, now I have mugwa is the tail, and sella mugwa, or no, fama mugwa is the head. So it's U3R mug both, fama mugwa and mugwa. And so U3R mug both is presumably the one that's screwy because U3R mug of two identical things gives you the same thing. U3R mug both. So it's like, let's take the left, let's take out the high bit of the right. Wait, sorry. Okay, so we're XORing a few things together. First thing we do is we take the right, we XOR it with with 31 bits of ones. We XOR that with the left, and then we mug it. What the heck? Isn't that trivially just? Well, no, because we XOR that should break the symmetry, right? Should break the symmetry. No, it doesn't. Isn't XOR associative? I'm not going to trust my brain on that. Is XOR associative? Like, yes. It's also, what the hell? I mean, it's also commutative. What the hell? Has this been broken since the beginning of time, or okay, what's happening here? Mix that. I mean, not cryptographic. Yeah, that's a bit of an understatement. I mean, it's obviously the same in the Hoon, right? Dang, what the hell? See, this kind of thing where you just need to like quick check or data driven, just be like, let me generate a bunch of things and see if they have the same mugs. Yeah, but I mean they have to have a similar shape, but still, like, I mean, we have lots of things the same shape. Let's just be like, okay, how many mug hashes do we have in my loom right now? That would be a good that would be a good check. Mugging your entire loom is like straightforward. They're mostly already mugged. They get mugged incrementally. Okay, if that's the bug, the like that basically the left and right sides are symmetrical, then um, we should be able to say mug of 1 2 3 4 1 2 3. That should be the same as okay, that I didn't predict. Ah man. Well, I mean, and the reason for that should have predicted that one, right? Because the reason for that, I find the Hoon slightly easier to read, but like, it's obviously the same. Well, actually, the C is just as easy, maybe even easier because it has the infix notation. Um, the reason for that is that if we take X and we XOR it with foo, and then with itself, like XOR is commutative, right? You can rewrite this as lefwa cat ritwa cat uh, this, and of course, what's X cat X? What's XOR with XOR? Uh, like what? It's nothing. Uh, okay. I mean that on the one hand, holy guacamole, that is like an incredible bug. Like that's incredible. But like for another thing, we use these hash tables, these mug-based hash tables, all over the place, everywhere. Now, I suppose that there's probably not that many cases where the left and right are like actually the same thing. That's probably why it doesn't cause that much of a problem. But if there's places like that in, I don't know, the bytecode cache uses these hash tables. Um, in the compiler uses these hash tables. I, it's absurd. I mean, yeah, there's the bug. I, it's absurd. But I mean, yeah, there's the answer. The question now is going to be like, uh, how do you fix this, right? You're like obviously you can fix it across a breach. There's actually another mug bug that I mentioned earlier that has to do with not clearing the mug when we edit a cell, which is really problematic, but is not related to this. And that's like just on a commit somewhere because we can't. You can't just trivially release that. You'll break everyone's everything. All the maps assume that mugs stay the same and so on. Um, so like you can breach. That's one way to do it. Um, Otherwise, you need to go through and find all your maps and rewrite them. Oh man. Okay. I mean, yeah. I mean that's the answer, and I'm sure that this is fixable. I I mean, couldn't we have chosen something that's like not associative, or at the least not commutative, but like, because like, is associativity sufficient? Yeah, associativity is sufficient to break the symmetry. Commutativity is sufficient. Well, no, it's the self-inverting nature that makes it so that if left and right are the same, it's broken. Oh, man, uh, oh man. I mean, if you just like subtracted them, that would have. I don't know. It gets weird, but like, man. I mean, the solution is probably pretty straightforward, and like if you ended up with actually having different mugs, then you wouldn't have everything going into the same bucket, and that part of pack would be fast. You might still bail meme because it's just maybe not enough memory, but like uh, the measuring would go fast. Wow, that's insane. Okay, I think I'm going to sign off. Hope that this actually recorded. Um, wow, shook. Okay, well, I guess we'll see this on GitHub issues. Wow. Okay, I'll see y'all later.